Thank you. Yeah, hi all, and thank you for joining. This talk will be about character encodings. ASCII, UTF-8, UTF-16. Unfortunately, character encodings in general are pretty boring and mainly annoying. So, for example, this. Probably a lot of you, at least non-native English speakers, have seen something similar. Some name contains a special character, like an umlaut character or a character with an accent, and they are totally messed up on being displayed. Admittedly, this guy here, Jürgen Großmüller, is pretty unfortunate with his names in terms of encoding, but this is not the only annoying thing about encoding. Are there any pen testers or red teamers here? Yeah? Okay. Maybe you also did something like this. A small script in Python 2 back then that uses a good old rock-UTXT to perform some brute forcing. So when running the script with Python 2, everything was fine. However, Python 2 was deprecated and Python 3 was released. With Python 3, the incomprehensible decision was made to handle strings as actual strings, which is super annoying. When running the script now, Python 3 just throws an error message that says something weird about UTF-8. The script doesn't work anymore. Pretty annoying, isn't it? But hold on, there is more annoying stuff. Are there any people with forensic skills here? Yeah, so my forensic skills are quite limited. If I want to search for a specific string in some files, I usually do something like this. A simple grep. Recursively look for files with a string matrix in it. Works like a charm and outputs this Linux binary, which contains the string. Unfortunately, though, I missed the second occurrence of the string in this Windows binary. It also contains a string, but it's encoded with UTF-16. Because of that, there are plenty of annoying null bytes here in the string, and my simple grep command just didn't find it. I don't know about you, but that's already enough for me, and we are on a tight schedule, so let's come to a final conclusion. Character encodings are boring. Dealing with them is very annoying. They keep us from doing our actual job in various situations. And after all, if some strange umlaut character is not displayed correctly, this does not have any security impact at all. However, I want to quickly show you something, a small demo. So we have some website here where you can enter a text. The text is reflected on the website itself. So what we do, of course, try our usual XSS payload. It's reflected, and it does not trigger. Having a look at the HTTP response, we can see that angle brackets are probably HTML encoded. So the payload don't trigger. What we can also notice is a script tag here with a lang variable, which is obviously populated from the query parameter we can also set in the URL. So let's try to escape the string by inserting a double quote and adding some payload here. But again, we can see it doesn't trigger. The double quote is escaped with a backslash. So the string context cannot be escaped. Now we enter some magic sequence. Boom, the payload triggers. And we see some weird Japanese characters here. So let's have a look at the HTTP response. Our double quote is still escaped with a backslash. So that's pretty strange, and the payload is here. But if you now have a look at the DOM tree, you can notice that, that there is no backslash anymore. Instead of a backslash, there's now a yen sign. So the double quote we inserted actually escaped the string context, and our payload triggered. So what the heck is going on here? Maybe this last point about security impact is not totally valid. With some weird character encoding behavior in the browser, we were able to inject JavaScript code. Before we explore what's happening here, a quick mandatory UMI slide. My name is Stefan. You can find me on Twitter or on X. I'm a vulnerability researcher in Sona's R&D team, the company behind SonarCube, SonarCloud, and SonarLint. Our vulnerability research team discovers zero-day vulnerabilities in popular open source software that we responsibly disclose to the vendors and use to strengthen our product with innovation ideas. So, character encodings. I think these emojis here describe pretty well how my attitude towards character encodings changed over time the more and more I learned about them. I hope that after the demo we are already in this mood. Obviously, there is more to characters encodings than just all this annoying stuff. So let's start very simple. What even is an encoding? There are different assets that we would like to store and process with a computer. For example, image, sound, text. The problem is that a computer cannot process these assets out of the box. The only thing a computer can process are ones and zeros. Thus, we need a way to map these assets to ones and zeros. The process of this mapping is called encoding. After the assets have been encoded to bits and bytes, a computer can process these. For an image, for example, we start with the first pixel and use some color module, usually RGB, which defines how specific colors mapped to bytes. In case of RGB, 3 bytes are used to represent the color of a single pixel. So we just need to look up the RGB value for our pixel, and we get the corresponding 3-byte sequence, which represents the color of this pixel. This byte can then be processed and stored by a computer. The same process is also required for a string. So we take the first character, and this time we don't want to map colors to bytes, but instead characters to bytes. Thus, we use some encoding scheme, for example ASCII, which provides a mapping between characters and bytes. We now only need to look up the character in this table, and we get the byte that represents this character. This byte can then, again, be processed and stored by a computer. So generally, very straightforward. So time for a small quiz. What do you think does this byte sequence represent here? I think I heard it somewhere there. So yeah, it looks like the string hello exclamation mark. But in this case, it's not. These are the RGB values of 2 pixels from this image. They just happen to have byte values, which are also valid ASCII characters. So the obvious conclusion from this is that we cannot decode a byte stream if we don't know what was encoded. However, we are really used to ASCII. Take a look at this hex dump, for example. There's obviously an A character here. The byte hex for 1 is always A. That's how it is. But in fact, the byte hex for 1 here has nothing to do with a character at all. This is part of an executable file, and the byte hex for 1 introduces an x64 opcode. Of course, hex dump is just the wrong tool here, and we should have used a disassembler, but there's kind of an unofficial rule which states, when in doubt, it's ASCII. I mean, instead of mapping single bytes to ASCII characters, hexdump could also map 3 byte sequences to a color. And that's how this would look like. It's just as valuable as looking at the ASCII characters decoded from binary data, which is not encoded in ASCII. So, of course, we need to know what data we are handling with. But in most cases, this should be very obvious, especially for image files with different file extensions that indicate what kind of data to expect. We have PNGs, BMPs, JPEGs, all of these 3 with different file extensions. This file extensions indicates that this is an image and what specific encoding should be used. But what about strings? We don't really have different file extensions, and strings are also used in memory and as part of network protocols. Do we even have different kinds of strings? Let's have a look at an application everyone here is using. Every day, probably for hours, a web browser. These are just a few of the character encodings supported by all modern browsers. But what is the big difference? Let's have a look at 2 of the more common ones, UTF-8 and UTF-16. Imagine we receive this byte sequence, and we know that it's a string. But which specific character encoding was used? Is it UTF-8, and the sender just wanted to warmly welcome us with these 2 emojis here? Or could it be UTF-16, and the sender is heavily insulting us in, I guess, Chinese? We don't know if we don't know their character encoding. And the fact that we usually try to stay in our ASCII comfort zone blinds us from the truth, which is very well summarized by this quote. There ain't no such thing as plain text. The quote is from Jules Bolsky, who wrote a very great article about Unicode and character sets in 2003, which is still absolutely relevant today. If you have a string in memory or in file, you need to know the encoding, or it cannot be correctly mapped to the information it's holding, the characters. The false assumption of the existence of plain text also hides where character encoding and decoding actually happens. Let me give you a very simple example. Imagine this simple website where you can submit a comment. What actually happens if you push the submit button? Well, the text free your mind is submitted to the server, which stores it. But wait, it submits the text free your mind. How does free your mind look like on a network wire? We only have ones and zeros. So there needs to be some encoding. And this encoding is performed by the browser when we push the submit button. The browser encodes the text free your mind, puts it in an HTTP request, and sends it over the wire. Now the web server receives the byte stream containing our encoded text and can decode it back to the text free your mind. The logic and functionality of a web server is usually implemented in PHP, Java, Python, JavaScript, or a similar language. All of these languages differ in terms of how they handle strings, but what they have all in common is that they need to store strings in memory. Yeah, and guess what? We cannot store a text in memory. We can only store bits and bytes. Thus, the text needs to be encoded again. And the encoding used here differs from language to language and is totally independent of the encoding used by the browser when sending the request on the wire. So now the string is loaded into memory, the application can perform some string manipulation on the comment, and once this is done, the comment should be stored in a database. Thus, it needs to be submitted over the wire again. And the encoding used here is again totally independent of the encoding internally used by the programming language. So the bytes in memory needs to be decoded and re-encoded before they can be sent over the wire. Now the database server receives this byte stream, can decode it back to the text free your mind. Yet again, the database server needs to store the string in memory and thus needs to encode the text independent of the on-the-wire encoding. At last, the text should be stored on the hard disk of a database server. Thus, it's decoded from memory and re-encoded with the character encoding used for the file storage. Again, an independent encoding. So that's it. Finally, the comment made its way from the browser to the hard disk of the database server. And this is quite an adventurous journey for the little comment. It passed through plenty of encoding and decoding steps. All these steps pose the risk of potential character encoding issues. But what even are character encoding issues from a security point of view? If you're a pen tester or red teamer, you've probably seen strange payloads like this. For example, for path traversal, there are these payloads which use some weird non-ASCII characters. And also for SQL injection, there are similar strange-looking payloads. You should always test these sequences. They just never work. But if we can figure out what the fundamental problem here is, we might be able to discover similar issues. So we already know the basics of encoding in general. So let's have a look at character encoding specifically. In fact, character encodings are quite old and were even used before the digital age. This is one of the first kind of chat application, a telegraph and the Morse code for character encoding. The core principle is straightforward. Characters and numbers are mapped to a sequence of dots and dashes. This way it's possible to transmit these via telegraph. Now fast forward to the digital age and to the rise of computers. Computers are awesome, and manufacturers are eager to provide great products. As with all fast evolving technologies though, there is a lot of competition and not much time for coordination. So each manufacturer came up with their own character encoding solution. These solutions worked perfectly fine as long as everything stayed within an isolated environment. But as soon as data needs to be exchanged, this became kind of a problem since these solutions were incompatible. It also slowly appeared that these connecting of computers might be the thing in the future, so we need some standard. The answer to this was ASCII. All letters are covered, all numbers are covered, there are additional symbols, and we even have control characters. Pretty solid solution. Unfortunately, somebody realized that there are more languages in English, and these use kind of weird other characters which are not covered by ASCII. So it became obvious that ASCII is not enough. But no worries, ASCII is a 7-bit encoding. This means that the most significant bit is always 0. Let's just set this bit to 1, which allows us to encode another 128 characters. This is not enough for all languages, but we can map the bit sequences where the most significant bit is 1 to different characters for each language. And that's how the result of this looks like, the ISO 8859 standard. For each language, there are different substandards that are compatible with ASCII and just use the additional 128 code points to encode the language-specific characters. But again, in terms of compatibility, this was not the perfect solution. When exchanging data between systems, there was still a lot of potential for confusion. Also, in the 1980s, additional character encodings emerged, which cover Asian characters for China, Korea, and Japan. These encodings, too, were limited to these specific languages. So the confusion was perfect, and the situation seemed pretty hopeless. But then the savior emerged, Unicode. Unicode assigns code points to practically every character from all major languages and writing systems. The latest version roughly contains 150,000 characters. It includes control characters, additional symbols, emojis, so pretty much everything covered when it comes to string. This is the character set used today and probably also during the next decades. Unicode itself only maps characters or symbols to code points. So whenever you see this U plus followed by a hex value, that's a code point. You can map a code point to a character, but it does not tell you how it looks like on the wire or memory or in a file. For this purpose, we need a specific character encoding. And for Unicode, the major encodings are UTF-8, UTF-16, UTF-32. Let's start with the most simple one, UTF-32. UTF-32 is the most straightforward encoding because it uses 32 bits or 4 bytes for each character. Because of that, it can directly use the code point values. So the A character, for example, is encoded with a 4-byte sequence hex for 1 followed by 3 0 bytes. This directly matches the code point value. The order of the bytes in memory are just the reverse because in most cases the little endian is used. The second character is also encoded with a byte sequence that matches the code point value. The same thing can be applied to the third character. The byte sequence just matches the code point value. So UTF-32 is very straightforward, but the downside is that we always use 4 bytes for each character. If a string only contains ASCII characters, like the symbol A character, there are 3 0 bytes that are totally wasted. UTF-16 tries to partially solve this with a more memory-efficient approach. It uses a fixed amount of 2 bytes per character. So for the A character, the code point value is taken again and put into a 2-byte sequence. This also works fine for the second character. The code point value fits into 2 bytes. However, for the third character, we've kind of a problem. The code point value does not fit into 2 bytes. And this is true for all code points that are not part of the basic multilingual plane and have more than 4 hex digits. So, for example, this emoji rocket here. These characters are encoded as something called a surrogate pair. A surrogate pair consists of a high surrogate and a low surrogate. These surrogates are just specific code points designated for the purpose of encoding characters that don't fit into 2 bytes. Each of the surrogates itself can be stored in 2 bytes. Thus, the total amount of bytes required to store this character in UTF-16 is 4. And that's everything you need to know about UTF-16. Fixed amount of 2 bytes per character, and characters with a code point that does not fit into 2 bytes are encoded as a surrogate pair. For ASCII characters, UTF-16 is still not the perfect solution. Not as bad as UTF-32, but there is still one completely wasted null byte. And a lot of strings only contain ASCII characters. UTF-8 tries to solve this with an even more flexible approach that uses 1, 2, 3, or 4 bytes per character. How does this work? We already mentioned that ASCII is a 7-bit encoding, and the most significant bit is always 0. For these bytes, UTF-8 does not change anything and simply matches ASCII. So the A character is encoded with a single byte hex for 1. The great advantage of this is that you can take an ASCII encoded byte stream and decode it with UTF-8. It will still result in the same characters. A 1 in the most significant byte is used to introduce a longer byte sequence required for all other characters. 2 leading 1s into 0 designates a leading byte which introduces a 2-byte sequence. 3 1s into 0 introduces a 3-byte sequence. 4 1s into 0 introduces a 4-byte sequence. And all bytes following in such a sequence are called continuation bytes and always begin with a single 1 and a 0. So we can either have a 1-byte character, which is equal to ASCII. We can have a 2-byte sequence, a 3-byte sequence, or a 4-byte sequence. All these remaining yellow bits here are not used for meta information and can be used to encode the actual code point value. This allows UTF-8 to encode over 2 million code point values, so far more than are actually assigned by the current Unicode standard. For example, let's have a look at this non-ASCII character. This character is encoded with a 3-byte sequence. This is a binary representation of these bytes. The first byte begins with 3 ones and a 0, so it's a leading byte for a 3-byte sequence. Thus, the next byte begins with a single 1 and a rich 0, thus it's a continuation byte. And also the third byte is a continuation byte. Each of these bytes contains 3 yellow bits, which can be used to encode the actual code point. So this byte sequence matches the bytes hex 7D, hex 20, which is the code point of this character. And that's everything for UTF-8. Single ASCII characters are just taken as they are. The most significant bit is used to introduce a multi-byte sequence of 2, 3, or 4, and all these byte sequences start with a leading byte, followed by a continuation byte. If that still feels a little bit confusing to you, I recommend to give a look at this UTF-8 visualizer I built to help understand how UTF-8 works internally. The tool allows you to enter text, binary, hex, and will encode and decode your input with UTF-8. This way you can play around with UTF-8 and or directly on a bit level. I will share the link later. Okay, so that's basically all we need to know to finally break something. I've picked 4 major security issues that you may encounter when dealing with character encodings. These are definitely not the only issues that exist, but this choice should give you a very good understanding of what can go wrong. We will cover overlong UTF-8 sequences, invalid byte sequences, string length issues, and encoding differentials. And if you listen carefully, you might be able to understand what was going on in the demo I showed at the beginning. Let's start with overlong UTF-8 sequences and have a look at one of the weird paths traversal payloads we already mentioned, this one. In binary, the first byte looks like this. There are 2 ones and a 0 at the beginning. Thus, this is a leading byte for a 2-byte sequence. So we need another byte. This is the next byte in binary with a single 1 and a 0 at the beginning. Thus, this is a valid continuation byte. Both bytes complete the 2-byte sequence, and we can now combine them to the resulting code point. In this case, the code point is hex 2E, which is a dot character. But this character is a simple ASCII character, which can also be encoded with a single byte. These leading zeros here are not necessary. Still, this 2-byte sequence resides in a dot character. The next 2 bytes in the payload are the same. Again, a 0-padded leading byte and a continuation byte, which both represent the dot character. The next 2 bytes are also similar, only this time they encode a slash character, which again is padded with zeros to form a 2-byte sequence. So this payload is just a common path traversal sequence. The problem is that the flexible approach of UTF-8 allows ambiguous mappings. An A character, for example, can be encoded with a single byte like ASCII. That's what we would expect. But it can also be, when padded with zeros, encoded as a 2-byte sequence. Or we can pad it with even more zeros and make it a 3-byte sequence. Or we can add even more zeros and make it a 4-byte sequence. It always resides in the same A character. Okay, but is this even a problem? Let's determine in which scenarios this could be exploited. Imagine we have a web application which accepts a query parameter called path. Before the query parameter is processed, it's verified that the value does not contain a path traversal sequence. In this case, that's fine, and the check is passed. Now, after this check, the value is UTF-8 decoded. In this case, the 2-byte sequence, hex C3, A9, is probably decoded to the accent E character. Now the application processes the string to access some file. If we try to use the classical path traversal sequence, the path traversal check fails and our input is rejected. If we instead use the overlong UTF-8 path traversal sequence, the check succeeds. Now the input is UTF-8 decoded, and the resulting string actually contains the dot slash sequence. This string is now processed by the application and may allow us to access arbitrary files. And this exact vulnerability affected Microsoft's IIS web server. In that case, it was even worse because you could actually traverse to system32 and run cmd.exe with a single GET request. So I won't guarantee that something like this couldn't happen today, but to be fair, that was in the year 2001. so 23 years ago. And the vulnerability was even added to the RFC of UTF-8. The RFC explicitly mentions this overlong sequence and also defines sequences like these illegal. It also mentions that this is a real threat and was used to attack web servers in 2001. So generally, you would assume that this is not a thing at all nowadays. But the reality is that there are plenty of custom UTF-8 parsers out there, and a lot of them are not compliant with the RFC. Let's have a look at an example for Java itself, specifically Java's deserialization. Let's imagine we have a simple class called evil class. The class is serializable and has a private attribute called CMD. We can create an instance of this class and set the CMD attribute to some malicious value. When this instance is serialized, the resulting byte stream looks like this. We've got the class name here. Here's the name of the attribute, followed by the type of the attribute, string in this case, and also its value. So obviously, all these strings are encoded in ASCII. Or maybe not. This is the OpenJDK implementation of the object input stream, which is used for deserialization. The method used to decode a single character is called read UTF-char. This is kind of UTF-8, but slightly different. At the beginning, the first byte is read. Based on the upper bits of this byte, one of the following switch case statements applies. We can either have a single byte character, a 2-byte sequence, or a 3-byte sequence. 4-byte sequences are not supported, so this is already different from actual UTF-8. In the single byte case, the byte value is just taken as is, since this is equal to ASCII. In the 2-byte sequence case, there's a check that the second byte is a valid continuation byte. However, when the call point is calculated, there is no check for overlong sequences. And the same thing is also true for 3-byte sequences. There is no check for overlong sequences. So let's assume we have an application that is prone to a deserialization vulnerability, but we cannot get our evil class payload through because a firewall or IPS detects this payload and blocks it. In order to bypass this, we can simply take our deserialized payload and change the first character of the class name to an overlong UTF-8 sequence. We could also hide any other string, like the malicious command. The modified data still deserializes to the exactly same evil class instance as before. When we send this payload to the application now, the firewall inspects it and doesn't find any malicious input. Thus, the payload is passed through and is eventually deserialized. So in summary, if you notice that a custom UTF-8 parser is used, check for overlong sequences and determine where in the data processing chain the parser is used. You can also use the UTF-8 visualizer to craft specific overlong sequences. It recognizes these sequences and shows you what character such a sequence would represent. Okay, an overlong sequence is technically possible, but just forbidden by the standard. However, there are also byte sequences that directly violate the way UTF-8 is working. For example, this byte sequence here. In binary, the sequence looks like this. The first byte is a leading byte, which introduces a 4-byte sequence. Thus, 3 continuation bytes should follow. The second byte is a valid continuation byte, but the third byte, it's not. It's a single byte which represents a character itself. How should we handle this? Discard the incomplete sequence, decode the single byte, or assume that it's a corrupted continuation byte and fix it? A lot of questions when dealing with an invalid sequence. So what does the RFC say about this? Implementations of decoding algorithms must protect against decoding invalid sequences. Sounds like a plan. So let's see how this works in real life and have a look at a popular web application, Joomla. Joomla is not as famous as WordPress, but with roughly 2% of all websites on the internet, there are still millions of deployments out there. At the beginning of this year, we disclosed a critical cross-site scripting vulnerability in Joomla's core filtering module that was actually caused by a bug in PHP itself. So to prevent against XSS attacks, Joomla sanitizes all input. Let's assume we have this string with a malicious script tag. Before the string is displayed, Joomla removes all HTML tags. The resulting string is safe to be displayed. So how is this sanitization performed? At first, Joomla is unaware of the structure of the input string. Now, the position of the first opening angle bracket is determined. Each character before it is considered safe, since it's outside of an HTML tag. All following characters, up until the closing angle brackets, are inside the HTML tag. This portion of the input is dangerous and is removed. The following characters up until the next opening angle brackets are safe again, and at last the characters until the closing angle brackets are also removed. The resulting string does not contain any HTML tags and is safe to be displayed. Now have a look at this part of the implementation. It uses PHP's MB string functions to process the input string. These functions properly handle UTF-8 and allow the usage of all Unicode characters. So, for example, it's possible to correctly determine the index of this evil emoji here. In this case, index 2 is returned because there are 2 other emojis before it. For this to work, the function needs to pass UTF-8 multibyte sequences. In the Joomla case, MB string pos is used to determine the position of an opening angle bracket. If this character is present, the index is passed as a length to MB substring to extract all characters before it. So exactly what we've just seen. First, determine position of an opening angle bracket with MB string pos, and then extract all characters before it with MB substring. The extracted characters are outside of an HTML tag and are thus safe. Now let's see how MB string pos and MB substring handle invalid UTF-8 sequences. We've got this byte sequence, and there is an opening angle bracket here. When MB string pos processes this input, it starts to pass the sequence from the beginning. The first byte is the leading byte, which introduces a 4-byte sequence. Thus, 3 continuation bytes should follow. Here's the first continuation byte, but the next byte is not a continuation byte. MB string pos still needs to somehow map the byte sequence to an index. So it considers the invalid sequence 1 character. This character is assumed to have the index 0. The next byte is a valid single byte, so it gets the index 1. The next byte is also a single byte, so it receives the index 2, and so forth. So from the MB string pos perspective, the input string looks like this. The opening angle bracket is at index 4. Now let's have a look at MB substring. It operates on the same byte sequence and starts to parse it from the beginning. The first byte is the leading byte for 4-byte sequence, so 3 continuation bytes should follow. But at this point, MB substring takes a little small shortcut. After all, it only needs to cut off the string at a specific offset, so it doesn't really care about the value of the continuation bytes. Thus, it simply skips over the next 3 bytes. These should be continuation bytes, right? This means that the 4-byte sequence is considered 1 character and gets the index 0. Now a single byte follows, which gets the index 1, another one, and so forth. So from the perspective of MB substring, the input string looks like this. The opening angle bracket is at index 2. So there's a significant difference between both functions. The invalid byte sequence can be used to shift the index used to extract the safe input beyond the opening angle bracket. The result is that the safe data can actually contain an opening angle bracket and also a whole HTML tag when adding more of these invalid byte sequences. Since admins can customize Joomla's PHP templates, it only takes a single click from an admin to achieve remote code execution with this bug. So let's see this in action. So here the attacker prepares a Python web server to host the JavaScript payload and also starts the netcat listener. And now only an admin needs to be tricked into basically just clicking on a malicious link. So here in this case via mail. Very obscure. So of course the admin clicks, and now it goes pretty fast. A PHP template is changed and arbitrary PHP code is executed, and the attacker basically immediately receives the reverse shell. Okay, so far we've looked at overlong and invalid byte sequences. But things can go even badly wrong for perfectly valid byte sequences when it comes to string length calculation. This works very differently from what you might have expected. We just had some PHP code, so let's have a look at some Python. In Python, the function len can be used to determine the length of a string. Unsurprisingly, a single A character has a length of 1. The same thing is true for an umlaut character, and also this single cup of coffee, and also this bug character. We can do the same experiment with Java. A single A character has a length of 1, same here, same here, same here. Wait, what? The single bug character suddenly has a length of 2. And when doing the same experiment with JavaScript, we can see that the bug character also has a length 2 here. How can a single character have a length of 2? To understand this, let's go back to our initial example. This time we are specifically interested in this part, the internal encoding used by the programming language. As already mentioned, a programming language needs to store strings in memory, and the memory can only hold 1s and 0s. Thus, the string needs to be encoded. And the internal encoding also affects how a programming language usually defines the length of a string. Python 3, which uses an UTF-8 encoding, returned 1 for the single bug character. Java and JavaScript returned 2. The reason for this is that they define the string length as the amount of code units, not characters. So in UTF-16, a simple A character is encoded with the 2 bytes hex for 1, 0. These 2 bytes are 1 code unit, thus the length is 1. If we now take the bug character, for example, 2 bytes are not sufficient anymore. This character is encoded with a surrogate pair. Each of these surrogates is encoded in 1 code unit. Thus, we have 2 code units and also a length of 2. This behavior can also be observed when calling split on a string in JavaScript. So for an A character, split returns an array with 1 element, the A character. So no big surprise here. But for the bug character, split returns an array with 2 elements, the high surrogate and the low surrogate. So it makes sense that the string length is 2. When an application does not account for the specific behavior of string length calculations, it might introduce severe security vulnerabilities. One of these is an interesting parser differential in Apache Guacamole, which I already presented at Hexacon last year. The gist of it is that Guacamole has a client component and a server component. The client is written in Java and the server is written in C. Both components communicate via the custom Guacamole protocol. The protocol is pretty simple. A single message consists of different elements. The first element is the opcode, which specifies which instruction should be executed, and the following elements are arguments to this instruction. Each element on its own consists of a length followed by a value, which contains 5 characters in this case. A user is restricted and cannot send arbitrary instructions. However, there is one instruction called image, where user-controlled data is put into the arguments of this instruction. So these strings can be controlled. If an attacker now places 4 bug characters here, the length field will be populated with 8, because 4 bug characters are encoded with 8 code units. The attacker can now place this usual string in the following argument. From the perspective of the Guacamole client, the message looks like this: 1 opcode with 2 arguments. This message is now submitted to the Guacamole server. The server is unaware of the structure and begins to parse the sequence. The first digit here denotes that 5 characters should be read. So 1, 2, 3, 4, 5. Opcode is complete. Read next digit. This time 8. So 1 character is read, 2 characters are read, 3 characters are read, 4 characters are read, and all bug characters have already been read. But only 4 characters were consumed so far. So more characters are read, 6, 7, 8. Now the argument is complete and the semicolon designates the end of the whole instruction. However, there is still data in the buffer, so the next instruction is read. The length field is 8, so 8 characters are read. 1, 2, 3, 4, 5, 6, 7, 8. And the instruction is complete. This is a whole new instruction which can be set to an arbitrary value. This vulnerability could be used to leverage specific guacamole instructions to read arbitrary files and even combine it with another vulnerability to get remote code execution. Okay, last topic, but really my favorite one, encoding differentials. Let's assume we have the string real, which is encoded using UTF-8. The resulting bytes can be seen here at the bottom. When these bytes are sent over the wire, loaded into memory, or stored in a file, the string should be decoded at some point again, which should result in the same string. This way, the very same string is restored. It contains exactly the same characters as the string before. This works fine because for encoding and decoding, the same character coding, UTF-8 in this case, was used. If instead of UTF-8, UTF-16 would have been used to decode the byte stream, the resulting characters were totally different from the original string. This mismatch between the character encoding used for encoding and decoding is what I'm referring to as encoding differential here. Such an encoding differential can basically happen everywhere. But let's have a look at a popular example, the browser and the web server. Our initial example outlined how a comment was submitted from the browser to the web server to the database server. So this is the direction we've been considering. Of course, all of this encoding and decoding steps are also required when viewing the comment. Just the other way around. The comment needs to be read from the hard disk of the database server, it's sent to the web server, and the web server serves the comment in form of an HTTP response to the browser. Now we are specifically interested in the part where the web server encodes the HTTP body and the browser decodes it. We've already seen that there are a lot of character encodings supported by a modern browser. When the browser receives an HTTP response from a web server, it needs to know which of those encodings it should use to decode the HTTP body. How does a browser decide which encoding to use? The most common approach, probably all of you are familiar with, is the content type header in the HTTP response. This header does not only contain the MIME type, but also an optional charset attribute, which indicates which character encoding should be used to decode the body. Okay, but what if the charset attribute is not present? In that case, the browser can check the HTML document in the body itself. There might be a meta text that indicates which charset to use. But this is already kind of a weird way to indicate a charset, because in order to read the HTML document, the browser needs to decode the body. So it needs to assume some encoding, try to decode the body, then check what the HTML document says is the actual encoding, and then potentially redecode the body. But there are even more ways to tell the browser which character encoding should be used. There's a special Unicode character which can be put at the beginning of a byte stream to indicate the character encoding. This character is called 0 whilst no break space, but is better known as byte order mark. So let's assume we want to encode the string new. These are the related Unicode points, and at the beginning we put the additional Unicode byte order mark. Now we use some encoding, for example UTF-16 little endian, to turn the code points into a byte sequence. When the byte sequence is decoded again, the corresponding parser only needs to check the first bytes to notice that we used UTF-16 little endian. Changing both of these bytes would result in an undefined character. So the byte order marker can be used to determine the byte endianness and also the encoding. For UTF-8, for example, the first bytes would look like this, which can be distinguished from UTF-16. This also works for UTF-32. The byte order marker is not specific to HTTP or HTML and is commonly used in files. But it also works for HTTP response bodies, and modern browsers support it. So there are 3 different approaches we've seen so far that tell a browser which encoding should be used. However, the charset attribute in the content type header is not always present. Especially for partial HTML responses, there's usually no meta tag. and the byte order mark is generally quite uncommon. So what should the browser do when there is no information on what encoding should be used? Well, it just tries to make an educated guess based on the content, which is called auto-detection. If it looks like UTF-8, then it probably is UTF-8. However, an attacker can easily influence the judgment of auto-detection by intentionally adding bytes that would result in reasonable characters in another encoding. And by the way, if you want to figure out which encoding the browser assumes, you can just enter document.charset in the webdev console. It will output the character encoding assumed by the browser. So let's quickly summarize the techniques that can be used to force an encoding differential between the browser and the web server. If you can control the first bytes of the body, you can insert a byte order mark. If you've got a header injection or can control the char set in the content type, you can directly set the encoding this way. If you've got an HTML injection, you can insert an HTML meta tag. And if no char set information is provided at all, which is really bad, you can leverage the auto-detection of the browser. OK, so now we can make the browser use an arbitrary character encoding. And there are quite a lot to choose from. However, most of these are ASCII compatible and not really useful from an attacker's point of view. There is one specific encoding, though, which is very interesting. ISO 2022 JP. This encoding is a Japanese character encoding that supports 4 different alphabets. It's an official part of the HTML standard, and it's supported by all modern browsers. What's really special about this encoding is that it supports certain escape sequences to switch between different character sets. So if a byte stream contains these 3 bytes here, they are not decoded to a character, but instead indicate that all following bytes should be decoded using ASCII. If a byte stream contains these 3 bytes here, the following bytes should be decoded using JISX 0201. And there are 2 more escape sequences which can be used to change the character set to 2 different versions of the JISX 0208 character set. One thing worth noting here is that common browsers like Chrome and Firefox will auto-detect this encoding if the char set information is missing and the body contains such a sequence. Another interesting aspect is that the later 2 character sets use 2 bytes per character. So these are not ASCII compatible. But let's have a look at an example. The default mode is ASCII. So if we decode this ASCII byte stream, we don't recognize any difference. In this case, the byte stream encodes the string, "Do not try and bend the spoon." That's impossible. Now, let's insert a few additional bytes in between this byte sequence. The byte sequence we inserted is the escape sequence to switch to the JISX 0208 character set. This means that all bytes following, which when decoded with ASCII represents the string "bend the spoon," now are decoded with JISX and become these Japanese characters at the bottom. There are also some question marks here because a few of these 2 byte sequences are invalid. So that's how our string looks like now. The text beginning from "bend the spoon" changed to some Japanese characters. Let's insert another escape sequence here. This switches the character set back to ASCII. Thus, the bytes representing the text "that's impossible" are correctly decoded again. This interesting feature of ISO 2022 JP seems very handy, but it can break some fundamental assumptions. I want to show you 2 different attacks that you can apply to any target for which you are unable to force an encoding differential via the outlined techniques. The first one is breaking HTML context. So let's assume we have a website where the user can enter text in Markdown. The Markdown is converted to HTML, but only a basic set of HTML elements is allowed. Thus, no JavaScript code can be injected. A user can, for example, enter this Markdown text. It contains a bold text and also an image. The resulting HTML code looks like this. For the bold text, the strong text is used, and the image was added via an IMG tag with its corresponding source and alt attribute. If a malicious user user tries to inject the JavaScript handler, this does not work because special characters like a double quote are HTML encoded and cannot be used to escape the attribute context. Now let's consider this markdown text. Just two images with the text in between. The resulting HTML code looks like this. Again, the images are added via an IMG tag with the corresponding source and alt attributes. When the byte stream is decoded with ISO 2022 JP, the default mode is ASCII, and everything is working as intended. We don't even notice any difference. Now let's insert an escape sequence in the description of the first image. This escape sequence will be placed in the value of the alt attribute. Thus, all bytes following until the end of the document will be decoded using JISX. This breaks the HTML document. Although this is already a denial of service attack, it does not yield the ability yet to execute our JavaScript code. But we can switch the encoding back to ASCII by inserting another escape sequence between both images. So now only two strange characters appear in the resulting string. If we look at the HTML syntax, though, we can notice something different. The beginning of the second IMG tag is now part of the attribute value. So what happened here? We inserted the first escape sequence within the attribute value, and the second escape sequence outside of the HTML text and the plain text. The 4 bytes in between the escape sequences are decoded with JISX. This also includes the closing double quote of the attribute value, which is now simply not present anymore. This means that all following characters are also considered to be part of the attribute value. The opening double quote of the second IMG tag now becomes the closing double quote of this attribute value. This also means that the second IMG source attribute is not an attribute value anymore. Thus, an attacker can replace the file name of the second image with a JavaScript error handler. This error handler is now part of the first IMG tag. This allows an attacker to inject arbitrary JavaScript code. The second technique can be leveraged to negate backslash escaping. The scenario for this attack is that some user input is placed in a JavaScript string. Double quotes and backslashes in the input are probably escaped, so it's not possible to break out of the string context. So let's imagine we have a website that accepts 2 query parameters, the search parameter and the lang parameter. You might be roughly familiar with this example. The search parameter is reflected here in the response, and the lang parameter is inserted into this string in a JavaScript context. Both parameters are properly sanitized. So for the search parameter, all HTML tags are HTML encoded, and for the lang parameter, double quotes are escaped with a backslash. Thus, it's not possible to inject JavaScript code. One of the possible char sets, which we have not covered so far, is a JISX0201 character set. In contrast to both other JISX character sets, it uses only 1 byte instead of 2. And that's how the corresponding code table looks like. The upper bytes here are used for some Japanese characters. And the lower bytes are, as usual, equivalent to ASCII. But if we look closely, there are 2 exceptions here. Both of these highlighted characters don't match with ASCII. For ASCII, the byte hex 5c represents the backslash character, and the byte hex 7e represents the tilde character. For JISX0201, both of these characters are mapped differently. Decoding the byte hex 5c results in a yen character, and decoding the byte hex 7e results in an overline character. So back to our web application. By default, all bytes are decoded using ASCII. If you try to inject JavaScript code by escaping the string context with a double quote, this does not work because our double quote is escaped with a backslash. But now let's insert this escape sequence in the search query parameter. This switches the character set for all bytes following to JISX0201. And this is how the browser sees the HTML document now. There is no backslash character here anymore, just the yen sign within the string. This means that the double quote we inserted actually designates the end of the string. And we can add arbitrary JavaScript code outside of the string context. Another ugly but yet so beautiful pop-up. So if you can make the browser assume an ISO 2022 JP character encoding, you can use these two techniques to get an XSS. What makes this so powerful is the auto-detection feature of the browser. An application with missing char set information is very likely to be vulnerable because you only need to insert an escape sequence to make the browser assume an ISO 2022 JP char set. From a security point of view, I hope that browsers will disable auto-detection for this encoding, and that's also what I suggested. Still, these techniques could be applied if you can control the character set directly via other means. Okay, I hope by now your mood changed to this. At least for me, it did. So let's give it another try and summarize character encodings. The first major observation is character encodings are basically everywhere. For all these places, there is potential for something to break. UTF-8 is the most common encoding, especially in the World Wide Web. However, there are plenty of legacy encodings which are still supported by all modern browsers. Not so much present in the World Wide Web, but still very popular is UTF-16. It's commonly used on Windows and also internally by a lot of programming languages to store strings in memory. And at last, we barely scratched the surface here. There are so much more vulnerabilities to be discovered, and I hope that this talk inspires you to don't just look away if you see some weird encoding stuff, but instead dive into it. It's really worth it. So thank you very much for attending and listening to my talk. If you are interested in more of this kind of content, feel free to follow us on X or Mastodon, and also check out our blog posts where we regularly release new articles on our vulnerability research. Furthermore, you can find the UTF-8 visualizer via the QR code here on the right. Thank you very much.
All right, thank you very much for the great talk. I think we still have time for one question. So, is there anyone wanting to ask something?
Maybe I can start with a question, and you got some ideas. So after your research, I get you're probably pretty sensitive to finding some partial differential bugs and stuff in the applications you look at. How do you usually start looking into this? Do you usually just try some certain sequences, or do you directly look into code, what decoder they use? What is your typical approach?
Yeah, mainly two approaches. Like one thing more dynamic approach to just get a feeling that something is decoded with some weird stuff. Like this is also like probably based on experience. And the second approach is to, if you are looking at white box targets where you have source code access, then specifically search for things like UTF-8, UTF-16. It's also like you can also, if you want to look for UTF-8 custom parsers, just there are some constants which are used when calculating the code pound value using UTF-8, and you can just search for those specific constants, and then you can quickly find places where custom UTF-8 parsers are used.
Oh, nice, thank you. So, any other questions?
All right, so then, thank you. We will just change a little bit, and then, we'll be back in a minute with the next talk. Thank you.